We're recording. I'm going to read the SI brochure, section 2.3, definitions of the SI units. Prior to the definitions adopted in 2018, the SI was defined through 7 base units from which the derived units were constructed as products of powers of the base units. Defining the SI by fixing the numerical values of 7 defining constants has the effect that this distinction is, in principle, not needed since all units, base as well as derived units, may be constructed directly from the defining constants. Nevertheless, the concept of base and derived units is maintained because it is useful and historically well established, knowing also that the IEC 80,000 series of standards specify base and derived quantities, which necessarily correspond to the SI base and derived units defined here. 2.3.1 Base units. The base units of the SI are listed in Table 2. Table 2. SI base units. Base quantity. Base unit. Name. Time. Typical symbol. T. Name. Second. Symbol. S. The symbols for quantities are generally single letters of the Latin or Greek alphabets printed in an italic font and are recommendations. The symbols for units are printed in an upright Roman font and are mandatory. See Chapter 5. Length, typical symbol, X, R, etc. Meter, symbol M. Mass, typical symbol M. Kilogram, symbol kg. Electric current, base quantity, typical symbol I. Uppercase or lowercase. Base unit ampere, symbol capital A. Base quantity, thermodynamic temperature, typical symbol capital T. Base unit Kelvin, symbol capital K. Base quantity, amount of substance, the typical symbol N. Base unit mole, symbol MOL. Base quantity, luminous intensity, typical symbol I with subscript V. Base unit candela, symbol CD. Lowercase. Starting from the definition of the SI in terms of fixed numerical values of the defining constants, definitions of each of the 7 base units are deduced by using, as appropriate, one or more of these defining constants to give the following set of definitions. The second symbol S is the SI unit of time. It is defined by taking the fixed numerical value of the cesium frequency delta nu sub capital C lowercase s. This does not have the letter V. It looks like it, but it's actually the Greek letter nu. New letter. In mathematics, for example, it's used to represent degree of freedom. To represent kinematic viscosity in fluid mechanics, one of the types of neutrino and particle physics. Okay. And this is the a symbol for cesium. The unperturbed ground state. Cesium, symbol CS. The unperturbed ground state hyperfine transition frequency of the cesium-133 atom to be 9, 192, 631, 770 when expressed in the unit hertz or H, capital H, lowercase z, which is equal to s to the minus 1 power inverse seconds. This definition implies the exact relation. The hyperfine transition frequency of cesium is 9, 192, 631, 770 hertz. Inverting this relation gives an expression for the unit second in terms of the defining constant of the cesium frequency. 1 hertz equals the cesium frequency over 9, 192, 631, 770, or 1 second equals 9, 192, 631, 770 over the cesium frequency. The effect of this definition is that the second is equal to the derivation of 9, 192, 631, 770 periods of the radiation corresponding to the transfer between the 2 hyperfine levels of the unperturbed ground state of the cesium-133 atom. The reference to an unperturbed atom is intended to make it clear that any definition of the SI second is based on an isolated cesium atom that is unperturbed by any external field, such as black body radiation. The second, so defined, is the unit of proper time in the sense of the general theory of relativity. To allow for the provision of a coordinated time signal, to allow for the provision of a coordinated time scale, the signals of different primary clocks in different locations are combined, which have to be corrected for relativistic Cesian shifts. See section 2.3.6. The CIPM has adopted various secondary representations of the second based on a selected number of spectral lines of atoms, ions, or molecules. The unperturbed frequencies of these lines can be determined with a relative uncertainty not lower than that of the realization of the second based on the cesium-133 hyperfine transition frequency, but some can be reproduced with superior stability. The meter, symbol m, is the SI unit of length. It is defined by taking the fixed numerical value of the speed of light in vacuum c to be 299 to 792, 458 when expressing the unit m s to the minus 1, or meters inverse seconds, where the second is defined in terms of the cesium frequency. This definition applies the exact relation c equals 299, 792 meters inverse seconds. Inverting this relation gives an exact expression for the meter in terms of the defining constants c and in terms of the defining constants the speed of light and the hyperfine transition frequency of cesium-133. 1 meter equals c divided by 299, 792, 458 seconds equals 9,192, 631, 770 c over 299, 792, 458. Cesium frequency is about 3.663 c over the cesium frequency. The effect of this definition is that 1 meter is the length of path traveled by light in vacuum during a time interval with duration 1, 299, 792, 458th of a second. The kilogram. The kilogram, symbol kg, is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant h to be 6.62070 times 10 to the minus 34 when expressed in the unit joule seconds, which is equal to kilogram meters squared inverse seconds, where the meter and the second are defined in terms of c and delta v and the cesium frequency. This definition implies the exact relation h equals 6.6260715 times 10 to the minus 34 kilograms meters squared per seconds. Inverting this relation gives an exact expression for the kilogram in terms of the three defining constants h, delta v sub cs, and c. 1 kilogram equals h divided by 6.6260715 times 10 to the minus 34, which is equal to 1 kilogram is equal to 299, 792, 458 squared over 6.6260715 times 10 to the minus 24 times 9,192,631, 770 h Planck's constant times the cesium frequency divided by the speed of light squared, which is approximately 1.4752 5214 times 10 to the 40th h, or the Planck constant times the speed times the Planck constant times the cesium frequency divided by the speed of light. The effect of this definition is to define the unit kilogram per the unit kilogram squared inverse seconds, the unit of both the physical quantities action and momentum. Determining the definitions of the second meter together with the definitions of the second and the meter, this leads to a definition of the unit of mass expressed in terms of the Planck constant h. The previous definition of kilogram fixed the value of the mass of the international prototype of the kilogram m of k to be 1 kilogram. Exactly the value of the constant Planck had to be determined by experiment. The present definition fixes the numerical value of h exactly, and the mass of the prototype has now to be determined by experiment. The numbers chosen for the numerical value of the Planck constant in this definition is such that at the time of its adoption, the kilogram was equal to the mass of the international prototype, m of k equals 1 kilo, with a relative standard uncertainty of 1.8 times 10 to the negative 8, which is at the standard uncertainty that combined budget estimates of the value of the Planck constant at that time. Note that with such present definition, primary realizations can be established in principle at any point
in the mass scale.